Okay. All right, let's begin. Hi, I'm Sean Owen. I'm a director of data science at Cloudera. I may know some of you in the room. I hope most of you know Cloudera. We provide a distribution of a bunch of open source software, including Hadoop, Spark, Kafka. And my role at Cloudera makes me do a lot of things. A lot of my days actually spent on Spark, for example. And we do talk a lot about technology since we're a technology company. And I decided I'm kind of tired of that. I wanted to talk about something different today. I wanted to talk about history and maybe try to make some comment on this question that keeps coming up, that what is data science? What is it we're doing when we say we do data science? What is my job? What am I doing here? I suspect some of you in the audience may have the same question because you too are a data scientist or are trying to create a data science team and don't really know necessarily how to think about it. So this talk is a little bit of a cheat. It's actually a talk about a paper, and they're both wonderful papers. So I'm going to narrate and maybe respond to a couple points in several good papers from the last 50 years. The paper that this is all really about is a paper from 1962 called The Future of Data Analysis by John Tukey. It's worth a read. Here's the link. You can go read it later. But it's interesting because the paper was fairly prescient, I would say. It was a critique of the field of statistics as practiced at the time. It's a long paper. It's about 60 pages, but I've excerpted a couple choice quotes here. We need to face up to more realistic problems, he says. Normal theory may only offer a framework in which some problems can be tackled simply or algebraically, and that may be a reason for starting with the normal case, but can never be a good reason for stopping there, and so on. So if you read the paper, you'll get the sense that he's criticizing statistics for being a little bit too theoretical, a little bit too concerned with the model and the math and the beauty of it rather than the practice of statistics as it really took place even in 1962. And that may be familiar to you if you are in the world of data science. It's supposed to be about machine learning and data and algorithms. In practice, it's all about computing and messy data and ETL and ingestion. So this, remember, was a comment made in 1962. And a lot of it is a call to action, that statistics needs to wake up and get a little more practical and focus more on learning from data, not just modeling it. And interestingly, at the end, he does actually even comment on the impact of the computer, which he says may be important but not vital. Okay, so he didn't get it all right. But he does at least acknowledge, even at that time, that there's something to computing and to the idea of implementing and engineering solutions that rest in statistics but aren't pure statistics itself. So I think it's fair to say that this was an important paper and a landmark paper. And it's the beginning of a point of departure for a lot of thinking in statistics that I think is at the root of what we come to know as data science today. The problem is that what we know as data science today didn't really all come from statistics. In a way, other fields came and co-opted some of what statistics maybe should rightly own. If you like, other fields like engineering drank statistics milkshake. This is data, this is statistics. And today we keep hearing about big data, we hear about data science, and we hear about this magical thing called machine learning. And I think a lot of statisticians are rightly wondering, what the heck? This is stuff we've been doing for 50 years or 100 years or 200 years. Why all of a sudden are people saying this is a thing, that this is new and it's hard to do and it's expensive and it's rare? Why is it that big data somehow is making this new? I think it is new, but it's worth examining why. If you look at the Venn diagrams people are drawing these days, apparently if you're a data scientist, you're not just 3 things overlapping, you're now 4 things overlapping. I found a 4-way Venn diagram for videos for data scientists. And so apparently it's data science is some combination of business acumen, programming, communication, and yes, statistics. So somehow we've convinced ourselves that data science is not just a subfield of statistics, but a superset of it. And I think some statisticians are rightly a bit upset about this. So along comes a paper last year that I really like, even if I disagree with parts of it. It's called 50 Years of Data Science. Maybe it should be called 53 Years of Data Science. But this is a paper that also points back to the Tukey paper as the beginning of the identification of a problem, if you will, in statistics. and a critique of how statistics has responded to that challenge and how big data and this big data meme has responded to that challenge too. I also encourage you to go read this paper. It's long, but full of good insight. But I'm going to summarize some key points from it for you today. So if you read through the paper, you'll first find that he makes some claims about why big data is all just a bunch of hype. And all this data science stuff we're talking about is really not important. The things we say are new, the things we say important about it are not actually that important, or at least they're not new. So number one, I think he claims that data science can't just be statistics on big data because statistics has always grappled with big data. Maybe. I mean, if you look all the way back, statistics is grounded. It came from an age where data was scarce, where the problem was that your sample size was 7, not 7 trillion. So maybe, but it's not obvious to me. He does cite the example of the US Census in the 50s. So it was really statisticians that created some of the first computerized systems for aggregating and analyzing the samples that made up the US Census. So some of this work was actually the genesis of some of the first times people used punch cards and mainframes for statistics. And he points to this as a good example of how the field of statistics itself has grappled with big data. I think that's true, although clearly this isn't statistics. This is computer engineering. So it's fair to say that statistics has been related to engineering, even if the field doesn't necessarily own the problem. I mean, this is actually, to me, a counterexample almost, an example of what pure statistics can't accomplish. We do need computing to scale up past some point. I think he even presents this example, 100 million people, as a modern big data problem. And I don't think 100 million is big anymore even. So maybe, interesting point. Another claim, data science can't be that interesting because if it's really just statistics on these new cluster technologies, surely that's not important because they're just so darn hard to use. And he points out my colleague Tom White's book, where he introduces the idea of taking the maximum of things as a way to introduce MapReduce. And sure enough, if you implement this in MapReduce, it's about 50, 60 lines of code. And of course, if you're using MATLAB or you're using R, it's a function call. Take the max of a vector. What's the big deal? How on earth can people do useful work on a framework like this if you have to write this much code to take a maximum? And I think that's maybe an unfair criticism because this is an example chosen to expose all the boilerplate you need to write a MapReduce. Not suggesting that this is a common MapReduce workload. I think we'd also find that if you're using a technology of the past couple of years like Spark, this is also a one-liner in big data technologies. And I think it also maybe misses the point. Yes, it's a one-line code in MATLAB, but how is that going to work if your data set is 10 terabytes? How is that going to work if it's 100 gigabytes, but it's not actually on your workstation already, and you have to wait to copy it? So I don't know. I think this is, there's a bit of a perception gap here. I'm not sure this is a great criticism of big data. But fair enough, it's been harder than it needs to be. Claim 2.3 in the paper, if data science is really just statistics plus some technologies, well, maybe that's true, but technologies come and go. Yesterday it was MapReduce, today it's Spark, tomorrow it's something else. It's only statistics that's constant. It's only the math and the analysis and the science that stays constant, and that must be the important part. Well, there's something to that. I think, indeed, even within the Hadoop ecosystem, we see it change quite rapidly year to year. But I'm not sure it's fair to say that stats is the only thing that matters. I think the fact that the tooling is growing so fast is a symptom of the fact that the value of data is growing so quickly, and we're adapting the tooling to scale up. I would point back to two famous papers on this point. One is the Banco and Brill paper that showed that at least in the early 2000s, adding more data made dumb algorithms beat smart algorithms on less data, roughly speaking. So their assertion was that it's probably better to invest in engineering better tools to get more data than necessarily research into ever more clever algorithms. And I think that's also the thrust of the unreasonable effectiveness of data by Norvig et al. Here, who from experience in Google assert that they got a lot of value, roughly speaking, from getting more data and processing more data and building tools to do that, rather than necessarily doing different primary research. So I don't know, yeah, tools come and go, but I'm not sure that's an argument that engineering is just a sideshow to data science. For the rest, a lot of the rest of the paper, I think, constructively backs up and tries to narrate some key points in the development of what we call data science now as it grew out of what we call statistics. And I'd like to summarize and point back to some of those milestones that are in fact interesting and do actually tell us a little bit about where we are today and put it in context of history. Number one, he points to the S language. I'm not sure if people know S as a language because it's from the mid-70s, but you will probably know its successor, R. So if you are a data scientist, you probably are accustomed to R, and you probably use it in a nice IDE like our studio here. And I wouldn't be surprised to hear that most people in the room also use notebook tools. And we take it for granted today. Of course we have an IDE. Of course when we do analytics, we have an environment in which we can combine data and scripting and visualization and share that as a unit. That wasn't always the case. It's not always been the case that statistics was done this way. A lot of statistics, maybe before this time, took the form of papers. Here's some analysis I did. Here's some data I'm not sharing with you. Here's how roughly the process I took, but I can't share that with you either. And this at least gave us a format and a paradigm for sharing both the research and the commentary and the visualizations and the output and the data as one unit. And that's a powerful idea that's endured and still endures today, I think, most, not only in R, but in the existence of notebook tools. So statistics has given us that, and that's a part of data science, no doubt. He also points to a paper called The Two Cultures by Leo Breiman. And Leo Breiman is probably best known for inventing, let's say, random forests. He's also a good writer, an observer of statistics. And this paper says a lot of things. Again, here's the link, read it later. But one of the biggest takeaways is mentioned in the title here. He said there were at least two cultures developing within statistics at the time of the early 2000s. One he called the generative modeling culture. The other he called the predictive modeling culture. The generative modeling culture was concerned with understanding why the inputs produced the outputs. What was the nature of the process or the distribution from which the inputs were drawn and from which the outputs were drawn given the inputs? It was more exploratory, trying to understand the process from the inside by modeling it. In contrast, he pointed to a very different goal, a very different subset of the field he calls the predictive modeling culture, that was much more narrowly concerned with making predictions. Not caring so much why the inputs gave the outputs, but simply getting very good at predicting the outputs given the inputs. In the paper, he said he believed that only 2% of the field were concerned with predictive modeling. And I would say that almost everything we think about when we talk about machine learning, when we talk about Coursera courses and Kaggle and so on, is actually predictive modeling culture. Very much concerned, I think, these days with our model accuracy. What's my ROC score? What's my accuracy? And that wasn't always the case, and that's not the only way of thinking about statistics. But for some reason, this has taken hold. This strain of thought has taken hold as what we call machine learning and data science. And it's interesting to think about why that is. But credit to Leo Breiman for maybe putting words around it. Next, he continues this point by pointing to another paper that outlines something called the common task method. And it's something that's so familiar to us these days that you'll wonder why someone had to put words around it. But it's interesting because it is not something we necessarily should take for granted. So if you are familiar with Kaggle, I think Kaggle is a great example of the common task method in action. So in Kaggle, the problem is framed thusly. Here's a data set. We don't care how you make predictions, but make predictions with your black box. And then we will score those predictions against some known correct answers and decide which black box is best. Clearly the product of a predictive modeling culture that prioritizes above everything else model accuracy. Is that bad? Some people would say that's bad. Some people would say that focus leaves out questioning why things happen and what is going on in a process. But on this paper narrates the flip side to that argument. So he talks about the development of machine translation in the 70s and describes research in the area as beset by glamour and deceit. He describes research as being set back by a preoccupation with theory, taking, for example, Noam Chomsky's theory of language and trying to translate that into a model that is somehow intuitively nice. The model itself seems like a nice explanation of language, and then trying to get accurate predictions out of it. Whereas the predictive modeling culture shifts the focus entirely to predictive accuracy. And once the field, he says, adopted this mindset, advances came quite quickly. Once people stopped being so concerned with how this was modeling language and just became concerned with accuracy of translation, suddenly things got a lot better, a lot faster. Maybe in the same way that the fact that we have SQL and we have standard benchmarks really has driven a lot of innovation in database design. It gives us a clear target to optimize, and surprise, people do optimize around that target. So I mention it again because it's not obvious that this is how we should do data science or how we should think about it, but it is, I think, how almost everyone in the room does think about data science today. And it's for some good reasons, but it's not the only way to think about it. Gaggle. So at this point, we're about halfway through his paper, and almost all of the rest of the paper is concerned with how we should teach data science. And it's a good read. I'm not going to actually go through a lot of it. He is, after all, a professor, and I think wants to come up with a good theory about what it is statistics should be teaching these days. That was actually Tukey's question as well in his original paper. What is it we should be teaching students as statistics? I think it's still relevant to a lot of us in the room, even if we're not students or we're not professors, because a lot of us are trying to understand what it is we need to be good at if we're going to be a data scientist, or we wonder what it is we need to, what skills we need in our organization in order to have an effective data science team. So I'd like to conclude by looking at his ultimate proposal for data sciences as a field of study, and then maybe compare and contrast that a little bit to what I think is going on in the field today. So he points, for example, to the UC Berkeley Masters in Data Science curricula. If you look at the curricula, there's 5 basic areas: research and design for data and analysis, exploring data, storing data, applied machine learning, okay, and then visualization and communication. Now, that seems pretty fair. As you can see, only a small piece of this is probably theory, or one of the 5 sections, and a lot of the rest is indeed about dealing with data, collecting it, understanding it, and communicating it as well. Fair enough. That is different than where we started 50 years ago. David Donoho eventually proposes a slightly different set of a slightly different curricula. His emphasis is a little more on the theoretical, I think. So doing meta-analysis, for example, science about data science, focusing a little more on modeling as separate from visualization and computing, and maybe spending a little more time on the idea of the representation and transformation of data. So this seems like an equally good or realistic view of what data science is today as a field of study. And it is more than just statistics. And it does seem to involve a lot of engineering. And I think a lot of what has been dismissed in this paper or in criticism as big data hype does actually have a lot of relevance to these points. If you in the room are doing big data, you're doing data science, I'm sure you do things that fall into these buckets. I'm sure your company sells tools that helps people do these things. So we're not that far apart, maybe. But in conclusion, I wanted to maybe compare and contrast this to what I see when people come up and say, can you help us do data science? Can you help us do data science to solve a fraud problem, for example? And as I wrote down all of the needs and the elements of a successful project that might produce a real fraud detection system, I realized it is still a lot more engineering heavy than maybe these proposals make out. All the time spent, if I actually listed where most of the time is spent in these projects, it's figuring out how to ingest the data, how to do real-time computation on data, how to serialize the data in a common way, how to version models, how to share data, how to do prediction in real time, how to learn not just over a small set of data, but a huge set of data, how to update that model incrementally now, not tomorrow, and finally, how to monitor it, how to know when it's gone wrong. how to know when it's making wild predictions, how to know when it's offline. So these are much more prosaic needs, I would say. But it does tell me that there's still some gap between what we think data science is in theory and what we know data science probably is, or at least I believe data science is, in practice. So to me, all this means is we still have a lot of work to do on the engineering end in order to get to this ideal. I'm not suggesting that we need to teach more. We're already teaching this in schools. This doesn't necessarily need to become the core of a data science course, but it does tell me that we, as a community, as vendors, as users, could still probably have an easier time with some of these prosaic needs in order to get back to all of the things that we should be talking about when we talk about data science and when we teach it and we discuss it. So that's on us. And that's, I still think, an open question to be discussed. So thank you. Now, I'll admit, I'm not 100% convinced about even all of my arguments here. And we have about 5 minutes left. If anyone's got a comment or a complaint about this discussion, I'd be interested to hear it now. If anyone's got questions, I'd be happy to talk outside as well. Questions, comments? Sir? We have roving mics, yes.
Thank you. Thank you for the talk. It's not a complaint, but a question. There is a trend in deep learning now when you just try to beat some benchmarks in images or in other data sets, and people don't care about some generalization theory or VC dimensions now and why deep learning works at all. What do you think about this trend?
So the question is, how does deep learning fit into all this? And interestingly, deep learning is an example of a model that's really not very interpretable at all. It builds this abstract feature representation that defies, usually, interpretation. So it's the ultimate in focusing on prediction accuracy. And you're right, we can take it too far. We can overfit research. If all of us are trying to score just a little bit better on ImageNet, is that actually doing the world any good? So I think that's probably a counter-argument to the focus on the common task method. And maybe one message is, maybe that's not entirely healthy to focus just on prediction accuracy, even if in a lot of contexts, yes, it does help. It is the thing that matters when we're trying to build better systems and more useful products for people. Down front here.
What do you think are the biggest challenges organizations face that are moving from your conventional relational analytics to big data?
So if people are moving from relational databases to conventional analytics and moving to big data, what's the biggest challenge? Probably a lot of it is skills gap. As much as we say that's just skills are just skills, technologies change. The set of technologies is in fact different when you go to big data. So there's probably a skills gap. There may be a little bit of a paradigm shift as well. Often in the relational world, the classic world, we have a relatively small amount of data and it's a fairly fixed amount of data. And the question isn't what other data do I want, it's what can I do how can I make do with the data I've got? And often the question in the world of Hadoop is, what would I get if I could get any data because it's cheap to store and it's cheap to process? So there's a little bit of a skills difference and maybe a little bit of a cultural difference. Just behind you.
Yeah, I just want to ask the question, like, if you split the data science, one part is the data engineering and the second part is the data modeling. Where do you see the most value at the moment? Do you think it's better models, or you still think that for many organizations it's the data engineering part to get the data working for them?
So where's the value? Data engineering or data modeling?
Exactly.
I think probably people need to do more data engineering just by percent of effort. And I think probably it's still true that new data, better data beats slightly better algorithms. So most of the work, most of the value you're going to get is probably in plumbing in new data sources or finally getting access to that data warehouse that you couldn't get access to before. And maybe doing that in a tight loop with people that are running the models and can help you explore and understand that these following data sources would be really helpful. So I think probably data engineering is still where most of the work is. Not that it's more important, it's just where more of the work is.
Hi. You told us about the history of data science, but what do you think about the future of data science?
Future of data science. In broad terms, I would hope that we have to it stops being so data engineering heavy, that this just becomes easier and easier. That as we standardize on tools and we stop having these different worlds of Python and R and Hadoop, that some of these problems become refactored and easier to deal with, so that we can, again, go back to focusing on the modeling and understanding what we're predicting and not just focusing on data wrangling. Deep learning is going to be a big part of that, one way or the other. Beyond that, I really don't know. Things change so much year to year. Time for one more, maybe? One more? Oh, good, okay. Was there one more over here? Question? Sir, in the middle? Or, sorry.
Hi, thank you for great talk. Just wanted to relate to your point about the seeming prevalence of sort of predictive modeling over generative modeling. And I'd like to relate it. I went a few days ago to Imperial College. There was a talk by Professor Mary Shanahan, who is a big expert on artificial intelligence. And he was sort of talking about the future of machine learning and artificial intelligence. And his view was that there seems to be much more success currently in the sort of deep learning and neural networks side of things, rather than what the AI experts refer to as symbolic AI, which is the more answering the questions of why certain outcomes appear out of the certain models, rather than the model efficiency and how accurate predictions these models actually make. And his view was that basically, because of the big data and because of the availability, there seems to be a view that because of the availability of a larger data sets, the deep learning neural networks sort of approach has become much more successful. And I'm just wondering if there is a correlation, because these disciplines very often in scientific world sort of influence one another, if there's any correlation, or indeed causation, no pun intended there, in those two fields. So that's the question and comment.
Sure, so whatever AI is, I don't think I'm an AI expert, so I'm not good to comment on that aspect. But to the point, why has deep learning been so effective? Why has big data been so effective? It is a little bit surprising that much brute force and that much data somehow does eke out not just marginally better results, but a lot better results. And what does that tell us about how we learn and think? So if image recognition does amount to a elaborate pattern recognition and doesn't actually consist in somehow, we aren't succeeding in modeling it with symbolic systems, what does that tell us about how we think? Are we just big pattern matchers, or does that give evidence for that theory of cognition rather than some symbolic system in our heads? That's a big question I feel maybe unqualified to answer, but you're right. Anecdotally, the effectiveness of big data and big computation is surprising. One more question over here, sir? Thank you.
Hi. So there are, as I see it, there are three main types of data scientists. People who teach themselves, people who have learned through working in a data science business environment, and people who have come off the back of masters in data science. I was just wondering how you would expect the skills gap to be different between the three, and how you would approach turning them into a more complete data scientist product.
So how does someone who's self-taught compare to someone who's come out of a formal program when it comes to data science? A good question. So I'm pretty much self-taught. I'm an engineer by trade. I've picked this up over the last, say, 10 years or so. So through a lot of self-study and a lot of mistakes, let's say. Is that a good idea? I think it's always good to learn by doing. There's no substitute for it. I do think it's like computer science. There's only so far you can get with just practical knowledge. For example, I imagine you can be an effective programmer without taking a course on data structures. But at some point, that's going to bite. If you don't understand how a hash map actually works, that's, at some level, that lack of that theory is going to bite. And likewise with statistics in general. You can probably figure your way through a linear regression package, but if you don't understand what Simpson's paradox is, for example, you're going to use it incorrectly and not know it at some point. So I think inevitably I think it's still a field where you do need some degree a formal background. Could be an online course. It could be self-studied, but I don't think it's purely pick up the tool and learn on the job by itself. Time for one more. Okay.
Hi there. So I have a background in data science, but now my focus is more about solving business problems, whether that uses data science or other types of analytics. And what I see a lot of the time is in the business community, a lot of sort of fear and lack of understanding, driving a lot of lack of adoption of the techniques where they could be applicable. So what experience do you have about sort of breaking down that lack of understanding, that fear in the business community about using these more scientific techniques?
Sure. So is a lack of understanding a barrier to adoption? Yes. If no one can agree what data science means, how do you go do it? I think the right response is to break it down and to demystify. So yes, a lot of what we do when we say data science is data engineering. So let's say that. And we can decompose the work we do into roles. And we can help people, we can help standardize tools and integrate tools so that it doesn't become this big bang change from one culture and one set of tools to another. So I do think there's a lot of confusion. I do think there's been so much noise and work going on in the area that I would be confused too. And I think it's going to resolve itself as people come to understand the reality of it, which is probably a lot of data engineering and little modeling. And as we kind of get better with tooling as well and bring the field to existing tools and paradigms rather than tell people it's something new and scary they've got to go embrace. So thank you very much. I'd be happy to talk outside.